Hello everyone. So today we will discuss regarding with and power amplifiers. So which will be model 3 in analog circuits. So you all know that is you have studied previous class, that is low signal amplifiers. So regarding with high withstanding power amplifiers, so we'll go for an low signal amplifier. Low signal amplifiers, in this, first of all, you have to know what is power amplifiers. So amplifiers which is used to withstand high power rates and which is used in communication receivers. These amplifiers are used. So in today's topics, we'll discuss regarding the definition and amplifier types, series feed amplifier, class A amplifier, transformer coupled class A amplifier, class B amplifier, class B amplifier circuit, amplifier distortion. So first of all, you have to know that an amplifier's classification. So the types of amplifiers is determined by its power. So it is classified into class A, class B, class C, class D, class E, class B push-pull amplifier. So by the collector current flows at the output, these are classified. Class A means that the transistor operates only during the positive off cycle of the input signal. Class B transistor operates only part of the positive off cycle. It is clear. So these amplifiers are used in power rating amplifiers. So ordinary transistor amplifiers cannot withstand huge power. So for that, a designer has designed a power amplifiers which is used to withstand high powers. So you can see here amplifiers, as I told, it is classified into class A, class B, class B push pull, class C amplifier, class E amplifiers. So you can see here class A amplifiers amplifies the signal. So what do you mean by amplify first of all? So amplifier is nothing but which amplifies a weak signal. To strengthen the weak signal, the transistor which is used as an amplifier. So power amplifiers circuits in this class A amplifier. So the output current will swings both positive and negative. So that is full 360 degree. So positive 180 degree, another 180 degree. You will get full waveform will be appeared, but the efficiency on this will be very, very less. So the designer has gone to class B amplifier. So class B amplifier, here the positive off cycle will be amplified and negative off cycle will be clipped off or chopped off. So you can see in the figure that is in class full positive and negative waveform with respect to T is seen. So whereas in class B DC bias level will be exactly across the zero level. So it will sink only 180 degree. So in this, an capacitor coupling is used, and also a direct coupled will be used. So what do you mean by coupling? That is, and one stage of the transistor or an amplifier is coupled with another stage which is known as coupling. Coupling is required in order to increase the gain of the amplifier. To increase the gain of the transistor, we will go for an coupling. So there are different types of coupling you will come across: capacitive coupling, direct coupling, emitter coupling, and the according to the and components is used. Coupling capacitor is used to an output stage in order to couple another stage of the transistor in figure 1. In figure 2, there is no capacitor or resistance in between a collector to base. So output of the collector of the Q1 is connected as an input to the next stage Q2. So the question draws the DC load line. So what do you mean by DC load line? We have studied this DC load line already in case of a transistor. So Q point is exactly less between an active region. So entire and waveform will be appeared across the output. So if you take an emitter configuration load line, so it will be appeared like across this. So IC saturation will be VCC by RC plus RE, and VC cutoff will be equal to VCC, and IBQ will be 40 microamps. Suppose if you take IBQ or an ICQ, so that is 40 microamps. So this is the biasing circuit of a transistor what we have considered here. So it swings I saturation to cut off region. So similarly, and this is a type of a feedback bias. So we have used power amplifiers. So in the circuit, and VCC is given. So here RC is connected across the output. So we can call that RC as a load, and collector current flows through the IC, and RB is connected to the base of the transistor. So high B is flowing. So for this, first you apply a DC bias operation. So the DC bias is set by VCC and RC. So IBQ equals VCC minus of 0.7 volts by RB. So how you can find out an IB current flowing in a junction? So it will be represented as IBQ. So how we can find out the current? That is potential difference between the RB. So what is the potential difference between RB? VCC minus of VBE. So VBE is the junction, transistor junction voltage that will be across base and emitter. It is clear what I am telling you. So IBQ is VCC minus of 0.7 volts by RB. So ICQ is nothing but beta times IBQ. So the collector voltage can also be written as the collector current, where you will represent with respect to VC, collector current with respect to ground. So we can say VCEQ. So how to find out VCEQ? Apply the KVL at the output. VCC minus of ICQRC minus of VCEQ equals 0. So finding out that VCEQ is equal to VCC, take VCEQ to the left side. Left hand side, if you take, that is VCC minus of ICQ into RC. Can I write like this? It is clear. So this is a circuit for a series fed power amplifier. Series fed power amplifier is nothing but RB is in series with the feedback to the base. So class A operation, the output of class A op-amp consists for the full 360 degree of the cycle. The Q point or bias level must be biased towards the middle of the load line so that AC signal can swing a full cycle. That is, DC load line indicates the maximum of and minimum limit set by the DC power supply. So class A operation, the output of a class A amplifier consists of conducts for the full positive and negative of cycle. So that is 360 degree. And Q point must be biased towards the middle of the load line so that the AC signal can swing a full cycle. DC load line indicates the maximum and minimum limits set by the DC power supply. It is clear. So class A power amplifiers is used so that you can amplify both the signals. So series fed class A amplifier. So when Q point is at the center of the AC load line, maximum class A signal can be obtained as shown in the figure. You can see here, if the output characteristics of a class A series fed power amplifier is drawn, and if you have selected the Q point, so AC load line, if you draw, AC load line means whenever an AC signal is given to the input of the series fed class A amplifier, whatever the output you will get from the output characteristics, if you draw the load line tangents to the IC as well as VCE, we'll call that as an AC load line. You can see here both AC load line and DC load line in this. So that is, and collector current saturation is represented by VCC by RC, or VCE cutoff can be approximately equal to VE, we can write. So you can see here how it swings in case of a series FET power amplifier. Series FET class A power amplifier. You can see here. So in AC load line and DC load line, the Q point for class A is at the middle of the AC load line. This allows for equal amount of swing that can take place on either side before going into saturation or cutoff. The fact that is always biased on the conducting makes it the most inefficient of all of the class of the amplifier. So you can see how the power amplifier input and output swings and how it is amplified and how you can see the Q point with this graphical representation. So amplified input and output stage signal variation. A small input signal causes the IB to vary above and below the Q point, which causes the IC to vary from the Q point set as well as the VCE. As the input larger, the out vary around the DC bias point until either the current or the voltage reaches a limiting conditions. IC will be equal to 0 and VCE will be equal to VCC. So if you want to find out the power gain in a series feedback, so power gain will be APS output power divided by input power. Power is represented P is equal to V by R. And AP is equal to AV square RN by RL. So if you know the formula of this, so that you can find out the output power. So how to find out output power? Output DC Q point will be equal to VCE into ICE. The power dissipation of an amplifier with no signal input is the product of its Q current and voltages. So series FET class A amplifier, for this you have to find out the efficiency. So series FET class A amplifier output power is power delivered to the load. We can write that as VCC maximum equals ICQRC, and IC maximum equals VCQ by RC. RMS value is, so maximum power out from class A amplifier. So P out max equals 0.707 IC into 0.707 VC, and maximum power out equals 0.5 ICQ into VCQ. 0.5 times current flowing across the collector and voltage flowing across the emitter. See here what happened. The efficiency of an amplifier is defined as the ability to convert its DC input to useful AC output. So the average power supply current ICC is equal to ICQ, and supply voltage is at least 2 VCEQ. Is clear? So if you want to find out the efficiency for a series feedback amplifier, so efficiency maximum is equal to P out by PDC. So P out, 0.5 into ICQ into VCEQ. So by PD is twice of ICQ into VCEQ. Is 25%. Say less amount of efficiency will be produced